Hi, everybody. Welcome to this webinar from Danfoss on how to increase overall system efficiency by utilizing heat recovery with your CO2 refrigeration system. If you have any questions during the presentation, where we will take some questions after each presenter has finished. Otherwise, we will take all the questions we can, there's time for in the Q&A session at the end of the presentation. But we have a lot of information for you today, so without further ado, I will switch over to my colleague Anja.
Yes, thank you, Anders. Hello, everybody. My name is Anja. I'm standing here in the Application Development Center here in Nordborg, which is the headquarters of Danfoss. Right now, I'm standing in what we call our mobile training unit because it is, in fact, a container that we can move around the world. In fact, it has been 3 times around the world already, and it will hopefully soon take off again. What we do here in the mobile training unit is that we simply demonstrate all of our solutions for CO2. Here, for instance, we have an example of a standard CO2 booster system. So for smaller systems, we have a solution for that with our CCMT light valve and our AKPC 572 pack controller and so forth. We have other applications in the mobile training unit here as well that we can demonstrate step by step, from having a normal transcritical system with an IT compressor, moving up to and having, of course, high pressure valves in that solution, moving up to having solutions with our ejector solutions in. We both have a high pressure ejector, we have a low pressure ejector, and we also have a liquid ejector. And with the liquid ejector, we introduced a new concept that we call CALM, that is CO2 adaptive liquid management, of course. And all of that is making CO2 possible all around the world. All of this we have been showing the world for quite some years now, and now we're ready to take the next step. Because when you have CO2 covered and you get it to run very well, then there is a natural next step that is including adding on heat recovery, which is the topic of today. What we have here is the mobile training units are set. So if any of you would like to have some training, then please reach out to Danfoss and we will see how that can happen either here in Nordborg or maybe this unit can come to you. But that was the introduction from my side. Now over to you, Mark.
Thank you, Anja. Let me share my screen. So, good morning, good afternoon, everybody. My name is Mark Sever. I'm a global application expert, food retail, and for many years, my main focus are different CO2 systems and mainly, of course, CO2 transcritical systems. Today, I will try to explain you a strategy, how we are controlling CO2 systems to manage to get the maximum out of CO2 systems to also produce heat. And later on, my colleague Dawid, he will explain you everything from the water side, what is happening. But first, I will go through the CO2 system. And this triangle is something I hope you will remember as a main message for the control strategy. So many of you, I believe, you have experience with CO2 transcritical systems, and you know that when you are above critical point, there is no anymore tight connection between the pressure and temperature, so we can go around this area quite freely, but having in mind and with a different focus in a normal operation, we are always trying to manage our temperature out of the gas cooler linked to the ambient temperature, and out of these two values, we are calculating what should be the pressure reference in the gas cooler. If we have a lower ambient conditions, we can go lower with temperature/pressure in the gas cooler. If ambient conditions are typically above 27, 28 degrees Celsius, then we are reaching the point where we are going into the transcritical area, and then we are trying to manage a system on this red curve. Just as a small note, if you are interested more about this red curve and you are familiar with our selection tool, Coolselector2, in all selections when its topic is CO2 components, you will have this option to select what is your temperature out of the gas cooler. And then if you go to the optimal gas cooler pressure, then you will automatically have a value what is here. Of course, in the control in the selection software, you can manage this pressure manually and then see how the system behaves differently. But let's talk about heat recovery operation modes. If you imagine you have a cold ambient condition, let's say winter time, all the temperatures, for example, below 5, 6, 7 degrees Celsius, we will be able to manage temperature out of the gas cooler on the level of 9%. If we follow this optimal COP line, we will be a bit lower with the pressure, but then there are some limitations on the compressors, and typically what we are using as a minimum pressure in the gas cooler in a normal operation 48, 40 up to 50 bars. So this is kind of typical settings. And if we have a system when we have a return temperature, water return temperature on the level of 27, 28 degrees Celsius, this will give us idea how much we can recover from the system. And for that reason, I put here a line of the constant temperature of 32 degrees Celsius, so you can visually see what is the area we can use for the heat recovery. When we are in these cold conditions, the amount what we can recover is quite small, so it's on the level of 8 to 10%. The temperature what we can reach on the discharge from the compressors is 50 degrees Celsius. In that, let's say, cooling mode, so we are not going to make a heat recovery, so we are going through these wells which are now open, and as I said, we are controlling the temperature out of the gas cooler based on the ambient temperature, and we are controlling these fans to be faster or slower, and the pressure in the gas cooler we are controlling with this high pressure expansion valve based on this pressure measurement sensor. But let's imagine we start heat recovery. What will be our first goal? And this is all a strategy controlled by the PEC controller, what we have in our portfolio. First, we will increase the pressure. And by increasing the pressure, you see this valve is now turned on, so all the mass flow goes through this plate heat exchanger. We are increasing possibility to recover. So from 8 to 10%, we now are on the level of 30% when we are reaching 65 degrees, 65 bars. What you can observe here that now this high pressure valve starts to operate more. I mean, it starts to tune this pressure in the gas cooler, but also your pump on the heat recovery side is also tuning to get out heat from the CO2 system. The fans very likely will be on close to its maximum operation because we are trying to reach this temperature out of the gas cooler on a low level. But of course, if ambient temperature is very low, then fans will tune not to have this value more to the left, because then you will have even more, you will have problems in your CO2 systems because you will not be able to control pressure in the receiver. If we imagine what will happen if we go further up, so we are now increased pressure in the gas cooler up to the 80 bars, and you can observe now that this area what we can recover is much bigger because of simply this these lines for the constant temperature are going in that way, how you see it here. This is maximum what you can get just by increasing your pressure in the gas cooler. It could be maybe 85 bars, then you will be slightly above, so you will have a bit higher heat recovery in percentage way, but you will not be able to gain a full heat recovery. So what we do as a next step? As a next step, we will start to increase reference for the temperature out of the gas cooler. This will result that your fans on the gas cooler will start to slow down. By slowing down, you will move this point back to this optimum COP line. What will happen during this process? Of course, your efficiency of your CO2 system will decrease. But here is also the main target to produce even more heat for your heat recovery system. And what is a typical challenge when you need mostly your heat for your supermarket or your store, your load on the refrigeration side is decreasing. So when we are moving this line here to this optimum COP point, we are decreasing efficiency of CO2 system. Your compressors will start to work more, so we will have a much higher mass flow through this plate heat exchanger here. At the end, we will be able to recover this full recover heat from your CO2 system. As a last stage, we can completely bypass gas cooler if we have this three-way gas cooler valve. So we will be completely recovered heat, not to be anything be released to the ambient. But what is important when we are doing this bypassing gas cooler, we have to switch control from this temperature, which is immediately mounted after the gas cooler, but to the one temperature sensor, which is after this connection from the gas cooler bypass valve. So this is a theory. How it works in the practice. So here we have a heat recovery unit, which Anja will show in a second. And there we have a controller which is measuring temperatures in the tank and measuring temperature on a discharge line to the consumer's side. And based on this temperature request, his controller is sending this request to our PEC controller, which is managing, of course, compressors, the high pressure valve, gas bypass valve, and also these three-way valves, what you have seen before. But how this request is acting in our system. So this is the whole strategy explained in, let's say, two diagrams. So if you look at the very bottom, this is a heat recovery request coming from this controller from the heat recovery unit. When it reaches 25%, then we are starting our heat recovery process. So we are, let's say, if we are below some pressure, I mean, for example, if we are running system on a 50 bars, and your minimum pressure in the gas cooler for the heat recovery is set on a 60 bars. So we will jump to this value. And in the log pH diagram, we will be on this point. So this will be starting point for the heat recovery. Further on, when the heat recovery request is increasing, what is happening? We are moving align this constant temperature isotherm, and the pressure is increased in the gas cooler. When we reach 55% heat recovery request, we will be exactly at this very top left part of this triangle, and this will be the maximum pressure in our gas cooler during heat recovery operation. Next step, when heat recovery request is increasing, what we are doing, as I explained, now we are increasing temperature reference out of the gas cooler. So we are going across this line here, ending up at this point, reaching to this optimum COP line. So this is a typical heat recovery process. Additionally, what we can do, if you have even more requests for the heat recovery. We can also bypass our gas cooler, like I explained. So we will completely minimize any heat transfer to the ambient. And at the very last stage, we can also enable additional heat sink or additional evaporator, which will create even more load in a refrigeration system, so we will get even more heat to be recovered. This is a all process what I wish to explain. Is there any question? If not, I will stop my presentation and we will come back to Anja. She will show us heat recovery unit live. Anja, please.
Yes, so I guess there's no question at this point, but don't worry. You can ask questions at the end and Mark will be ready to answer them, I'm sure. So welcome back here to the Application Development Center in Nordborg. Now I moved a little bit, you might have noticed. And now I'm standing in front of our heat recovery unit. Here we have a 2-tank solution that Dawid in a sec will tell you much more about. What I would like to bring forward to your attention is the frame of it, the module that it actually stands on here, because this is actually one of the secrets why we have such a big success with it, is because it can actually just be fitted in anywhere. It can go through any door, any port, and be installed in any supermarket, either retrofitted or being installed from the very beginning. We have this as a standardized solution from Danfoss, so we know how it all is connected together. We know how it all plays together, and we have a well-proven track record of it. It is with energy meters and heat exchangers and everything perfectly worked out together. In this standard electrical box, you will see that we also have prepared everything, and of course we have the ECL controller, which is the main brain in all of this solution here, and what is making sure the system runs as wished. But as you can see, I'm standing here still in our Application Development Center, meaning that if you were to learn more about this very nice solution, then you could come and visit me and my colleagues here in Nordborg, and we would be very interested in giving you an introduction to our heat recovery solution. You can try yourself to see how it all works together. Yes, I think that was it for me as the introduction. Now over to you, Dawid.
Yeah, thank you, Anja. I will just share my screen. Okay. Hi, everyone. My name is Dawid Lawreszuk. I am HRU project manager at Danfoss. Today, I would like to present you our heat recovery from CO2 cooling application. To make heat recovery easy and efficient, Danfoss combined our expertise in heating and cooling to create heat recovery unit. It is a prefabricated solution for heat recovery from CO2 refrigeration system. Recovered heat can be used for space heating, domestic hot water preparation, or can be sold back to the district heating network. It connects cooling, heating, and ventilation systems. There are 6 standard layouts based on supermarket size. It uses special buffer tanks to achieve good heat stratification for optimal heat recovery. HRU was designed to resolve supermarket pain points with heat recovery. So what are those pain points? In the past, heat recovery in the supermarket was not so common. Here we can see a typical situation when all heat generated by the cooling pack is dissipated to the atmosphere in the gas cooler. At the same time, heat was needed for space heating or domestic hot water preparation. In some countries, heat recovery was done in a simple way. In that case, 3-way valve and the heat exchanger are added to the cooling pack, and the heat consumers are connected to this heat exchanger. Most of those applications are made on site by installers, and each time they are made in a different way. Such systems often have poor regulation and insulation, which generate high heat loss. Also, heat is reclaimed only when there is a heat consumption. This creates high temperature fluctuation in the CO2 heat exchanger, which can shorten system lifetime significantly. HRU resolve all of those issues. It is a prefabricated solution, which is easy to install. It standardizes heat recovery across the stores, which is requested by supermarket networks. It is fully insulated and controlled, and by usage of buffer tanks, it can assure stable condition for the CO2 heat exchanger and can collect all available heat from a refrigeration system. It has also possibility to resell surplus heat to a district heating network. I will now show simple animation of HRU operating principle. During the operation of the CO2 cooling pack, heat absorbed in the cooling cabinets need to be rejected in the gas cooler to the atmosphere. To reclaim this heat, the discharge gas is directed by the three-way valve through the CO2 water heat exchanger. The water stored in the buffer tanks is heated up to the desired charge temperature. Once the water has achieved the required flow temperature, it can be used to deliver heat to the consumers. If heat available in the refrigeration system is higher than the demand of the utilities, then surplus heat is stored in the buffer tanks. If the consumption is higher, then heat is added from the buffer vessels. Until now, two solutions have been designed based on the store size. One tank solution for stores up to 1,500 square meters, and the two tank solution for medium and large stores. Both solutions can have direct or indirect connection to external heat source. In case of the two tank solution, there are additional variants with heat resale possibility. Our portfolio can cover heating demand from 22 up to 540 kilowatts, with possible heat recovery between 100 and 400 kilowatts. Until now, 115 units was installed across Europe. We gathered experience from installation in Denmark, Norway, Sweden, Finland, Lithuania, and Germany. Based on those experience, we know that the maximum payback period of the HRU was 24 months if without heat resale, and 18 months with heat resale. In 10 years, typical sized HRU can generate around 62,000 euros of savings if the primary heat source is district heating, and additional 23,000 euros if store resell heat to the district heating utility. We have a case study from a store in Denmark, which operated 1 year without heat recovery. It used during that period 150 megawatt hours of heat. Danfoss helped to optimize its heating system to reduce consumption to only 71 megawatt hours of heat. And then installation of the HRU reduced it by another 56 megawatt hours. On the graph, we can see the measurements made by heat meters installed on this unit. HRU covered 82% of internal heat consumption, and additional heat was both from the district heating utility only in cold months. In this case, if the operating pressure of the CO2 cooling pack would be controlled by the HRU, then full heating demand of the store can be met only with recovered heat. To achieve such good results, we need to fulfill some preconditions. First, heating system must be optimized. To ensure highest possible heat recovery rate, we need to lower return temperature from heating system to around 30 degrees Celsius. We can do it by sizing heat system with the right temperature level. And in the table, we stated maximum recommended temperature for the different heat consumers. Second requirement is to size heat recovery heat exchanger with right parameters. On the CO2 side, we need to use maximum pressure and mass flow expected during the operation of the refrigeration pack in transcritical mode. For those parameters, maximum temperature of the CO2 needs to be calculated. This temperature should be used as the inlet temperature for the CO2 heat exchanger sizing, and the outlet temperature should be around 5 degrees higher than the inlet water temperature. On the water side, input temperature should be design return temperature from your heating system. So as we said, it should be max 30 degrees. The outlet temperature should be the temperature at which we would like to store the heat in our buffer tanks. We recommend at least 40 degrees Celsius difference to ensure the bigger amount of energy to be stored. When we have design parameters for the heating system and the size of the heat reclaim heat exchanger, then we can size HRU in the Coolselector software. We need to choose the type of the unit from 6 layouts and then fill in the design temperature, and on that base, software is choosing the right code from 84 standard codes available in Danfoss store. Now I would just show how you can do it. So this is Coolselector2 software. We need to go there to the commercial applications. Then we need to choose the heat recovery unit. And then first we need to choose if we would like to have 1 tank design or the 2 tank design. Then the second option is to choose if we would like to have the direct connection, indirect connection, or direct connection for your external heat source. And with the 2 tank solution, we need also to mark if we would like to have the possibility to resell the heat. Software based on our selection, software is showing us the basic circuit diagram of the system. Now, if we would like to choose the right code, we need to put the parameters here. So first, we need to know what is the maximum supply temperature for the heating system. So we can say it's not 60, it's 50 degrees. Then we have the return temperature, and we need to know the heating demand of the system. If we put all of them, our software is calculating the required volume flow. And based on this volume flow, it's selecting the heating part of the system. And we can see here what is our selection and the capacity, and also the velocity of the water inside the pipe. And then also here, it's showing what maximum flow we can have to achieve in this, and the minimum one. And the same, based on that, we can adjust our refrigeration system. So this is charging temperature. So this is the value which I showed previously for the selecting of the CO2 CO2 water heat exchanger. So here we can say that it's not 70, it can be even 80 degrees. The return temperature, as I said, it should be the return temperature from your heating system. And then also we need to put the capacity. So we can also increase this to, for example, 200 kilowatts. And based on that, also our software is calculating the required flow. And based on this flow, also it's choosing the right code. And here we have the selected code. And with that code, you can just reach to Danfoss, and we can make a quote for you and assume the delivery dates for the system. Yeah. If you would like to know more about the HRU, you can visit the hru.danfoss.com, or where you have all of the information which we showed today, but also there are additional case stories from different stores in Europe. And also you can go to our heat recovery unit part in the Danfoss Global Product Store. And you can go also to the Coolselector2 software to make the selection of the unit based on your needs. Okay, and now I think we are going back to you, Anders.
Thank you to Anja, Mark, and Dawid for all the information of this very interesting product, and on how to optimize to get the full potential out of the heat recovery unit. If you have any questions, now it's the time to ask. We have our team ready here to answer any questions, hopefully, if we can, to ask any questions you might have. Otherwise, I'm posting some links now in the chat where you can read more about our CO2 solutions, as well as getting the entire case story from the supermarket in Denmark, the Menu supermarket in Denmark, but also a link to our heat recovery unit, where you can read much more and see much more information about the heat recovery unit. Yeah, so far you have done a good job explaining everything there is to know about the heat recovery unit and how to utilize this best possible, because not a lot of questions has come in so far. So if one of you who wants to elaborate on any aspects, there's also a possibility here. If not, then
So if you have any questions to me standing here in front of the heat recovery unit, it is also a good question if there's any aspects or details that you would like to ask while Anders is posting in the link into the chat function, then it is for sure possible. You can either chat them in the function, or you can raise your hand, and Anders can make sure to unmute you if you were to ask any questions or want to see any details more clear. Then we are here and ready to support you.
Looks like we were very clear. At least,
yes.
Anders, you'll answer this. So just not too late. So It looks like people understood what we were talking about. So,
job well done. Very good. We're happy
come to us if you have any project where you can think about heat recovery. So we will find a way what will be the optimum solution for your particular plant. Well,
yeah. Otherwise, yeah, reach out to our local sales teams if you want to know more. And as Anja mentioned previously, we have a functioning unit standing in Nordborg, Denmark. If you want to have a closer look and see how it works, or if you just need more information, reach out to your local sales teams, and we will do everything we can to address any questions you might have.
Anders, excuse me, there is one question. Is it also possible for other refrigerants? Yes, why not? So maybe to clarify, you saw these two tanks. Anja is showing them in live.
Yes.
So what is not included is this plate heat exchanger water refrigerant. This is something what you have to size and select separately. So in that respect, if you have some other refrigerants, then the plate heat exchanger should be applicable for these refrigerants. The controller on the heat recovery unit will send again heat recovery request to some other PEC controller, which will manage to increase probably pressure because all other refrigerants they are not going into this transcritical area. So based on this heat recovery request, you can tune your pressure in your refrigeration system. Is it ammonia? Is it some other synthetic refrigerants? So in principle, you can use it also for other refrigerants. So yes.
Just to say a little bit more about this topic is why the CO2 is so great for the heat recovery. Because of its operating temperature and the pressure inside, we can reclaim water at quite high temperatures. So between 60 and 80 degrees of Celsius. And this is enough temperature to cover all heating needs inside the store. So not only the heating, if you have low temperature, for example, floor heating or something like that, but also you can prepare the domestic hot water with that. With other refrigerants, with ammonia, it also operating with quite high temperatures, so we can more or less have the same there. But with other refrigerants, what we see is that the temperatures which we can achieve, even with higher pressure, it's between 30 and 40 degrees. So in that case, it's also fine to collect heat at that temperature, but then in many cases you need to have more external heat. So then you need to connect to the HRU, for example, the district heating, and we will just add it from this external heat source, just the amount of energy which is needed to rise this temperature from this 30 or 40 degrees up to required flow temperature. Yeah.
Good. Yes. Anders? Unmute.
Yeah, sorry. I don't see further questions. So yeah, if you don't have any further questions, then just want to say thank you so much for participating today, to listening in to us. And yeah, I posted these links where you can read more both about our CO2 solutions, but also the heat recovery unit, as well as this case story about from the supermarket in Denmark. So, and then again, reach out to our to our colleagues where you might be. And then, yeah, thank you very much for listening in and have a great day. That's all from us.
Thank you.
Thank you for
Bye-bye.
participating. Have a nice day. Bye-bye.